Hi everyone. Welcome to the Unsupervised Learning module of Amazon ML Summer School. I am Ayush Raj and I work as applied scientist at Amazon. I would be covering the part 1 of unsupervised learning, which would be about the significance of unsupervised learning, when do we do unsupervised learning, and also a domain of unsupervised learning, which is clustering. In clustering, in depth, I would be covering k-means clustering, hierarchical clustering, and DB scan, which are applied in different structures of data. Till now, you must have seen when we use supervised learning. Suppose you have some label data where you know which data point belongs to which label. For an example, over here, you can see that there is label data of ImageNet where you know that these images belong to this particular class. When we have this label data, we can train our model to recognize patterns in the input features, which in our case will be pixels of the image. And from pixels of image, we want to map it to the label. Which class does it belong to? When we have label data, we can train a model with some objective function because we have a label and it can learn for us the label mapping. The objective function can differ in case of regression or in case of classification. But suppose if we don't have labels for our data, which would be the case in many of the applications we have in real data scenario, but we have a lot of data. So even if there is lack of labels, we can learn some structures from our data and try to infer which data points can belong to which class, maybe. For example, we have so many videos on internet. We might want to cluster videos. Cluster means group videos into some categories, some categories, some categories, even if we don't have labels for each and every video that is over there. So suppose we have data points and we don't have labels. What are the kind of questions we can try to answer from data without having availability of labels? One thing can be we group those data points into some clusters, and we might want to say this belongs to cluster A, this belongs to cluster B. Or another thing can be we learn the whole story of the data. By story, I mean if I can learn the probability distribution that generated this data, I can generate new data points, which can be helpful for other applications as well, like creating more data for some supervised learning task, or by learning the probability distribution of my data set, I can even learn whether a particular new data point can belong to my data or not, whether that data point is an outlier or not. And there are numerous other applications which learning this P of X, which is probability distribution of our data, serve us to do. And next thing we can also do is we can learn some latent representations from our data. Because suppose we have images. Images have pixels which are largely unstructured. Suppose we have a person and we have some features corresponding to that person, the person's age, the person's weight, height. These are feature variables which are meaningful and structured, but image pixels are not structured. To make those pixel values meaningful mathematically, we would want to project them into some vector space which is meaningful mathematically. And projecting our images or any other data points to a particular vector space comes under representation learning. We want to learn some representations of our data which can be helpful for the final task I am doing. So this also serves as a form of unsupervised learning where I'm trying to learn something from my data which is hidden. And here you can find different forms of unsupervised learning from unlabeled data listed out. Clustering is grouping it. Anomaly detection is whether a particular data point is an outlier, does not belong to our data. And generative modeling, as I told it, like learning the whole story of my data, from where is my data being generated. And self-supervised learning is just a form of unsupervised learning where you create labels from the data itself. Like the language modeling you have in GPTs or BERT models have been trained using self-supervised learning. So yeah, like one question would be driving everything in this module is how can I explain my data when I don't have labels? Whether I should be grouping my data, whether I should try to learn the probability distribution of the data, or we can try to learn some latent representations which can serve the purpose for our use case. Let's see. And yeah, like just to clarify, unsupervised learning is not something very old school and classical, but this has made the foundation of the hyped AI era we are living in right now. You can see from the examples over here. So, if we talk about finding structures from our data, the most basic question is, can my data be grouped into something, which is clustering? And there are different clustering methods which can be applicable for different structures of data. Like k-means would try to find spherical blobs in my data. There is another method called DB scan which finds density in my data. And Gaussian mixture models assume that my data is mixture of lot of Gaussian distributions, and based on this assumption we try to group our data. Now let's move to clustering, where we will be finding those groups or partitions. And there are many applications of clustering, like we want to segment our customers to which kind of customers they are, or suppose we want to compress some images too, then we might want to assign some images into one particular cluster and another images into another cluster, which is kind of reducing the amount of memory I would use for storing those images. And these are some examples how clustering is used at Amazon. So we have different kinds of clustering. Like K-means is an example of centroid-based clustering, and hierarchical clustering is an example of connectivity-based clustering. So connectivity means which two clusters do I call connected? How do I define that connection? Because defining that connection is very important, as we'll see when we discuss about hierarchical clustering. And another one is density based clustering, where we don't assume my data or my clusters to be spherically concentrated to be in the same cluster, but we leave it free to estimate the density of my data set, and then we can find those clusters. Another one is distribution, where we assume that my data has a particular distribution, and with that assumption we try to make different groups. And also for clustering, you would want to define which 2 points of mine are close. Now how do we define this closeness depends on my distance metric. Suppose my distance, the most common distance is Euclidean distance, where you have two data points and you assume that the distance is just the shortest distance geometrically you can take between those 2 points. But that might not be the case always. Suppose the constraint from moving to one point to another point is that we can only move uh, at once through x-axis and then via y-axis. It's called Manhattan distance. Like you have grids in the city of Manhattan. So if the closeness has that constraint, I cannot go to this person's house without going through the roads connecting it. And you might also have p is equal to infinity. In case of p is equal to infinity, the distance is becoming the maximum distance along any dimension I have between these 2 points. For an example, you might consider, suppose we want to group some data based on whether like production of something has less delay or production of something has more delay or mid delay. Suppose we have multiple delay variables x, y, and z, whether the delay is in shipping of A or shipping of B or shipping of C, and we need three of these things A, B, and C to make something, supposed to make a laptop. Then I would not be adding up A, B, and C delays to get all of my delay, because these would be parallel tasks taking along. I would want to know the maximum delay which happens for anything, because everything would start at the same time and I cannot add them up because they are happening parallelly, and I would want to know the maximum time that any one of them took to know what I would be calling distance for this clustering problem of mine. So basically, how we define closeness is of importance when we are doing clustering. And another example of a distance is Mahalanobis distance, which is particularly helpful when we want to find whether this particular point belongs to my data distribution or not. For example, this is kind of a stretched distribution. I can't use spherical distance or Euclidean distance to find whether the point belongs there or not, because you can see A is having more distance than B, but you can clearly see that A belongs to our data set, but B does not. Now, how to have that transformation, that in a transformed space, we get point B as an outlier and A close enough. So, this distance, the Mahalanobis distance, helps us do that. And to understand it clearly, the basic thing is it does is I am transforming my basis vectors in the space in which I am observing distance. So, two things I need to do, I need to rotate and I need to scale my distances over here. So, in a transformed space where a Euclidean distance would be meaningful for knowing whether a data point belongs to my data distribution or not, this is what Mahalanobis distance does. It transforms this thing over here, is the whitening transformation taking place. Basically, you are transforming your rotating your basis vectors, and then you are normalizing by the variances you have along the new basis vectors, if you want to understand it with intuition. And in the transformed space, Euclidean distance of the transformed space can serve as a good metric for knowing whether a point belongs to my dataset or it does not. And in case when your data is not a vector, again, you can have different notions of distances, like in case of set, what part of the set is overlapping. And for example, in a time series, two time series can be compressed or stretched or moved, delayed with a shift, especially in signal processing. You might observe that there can be signals which are shifted but are similar. They have the same patterns, just there is a temporal shift. In that case, we don't want our distance metric to penalize these two signals just for the temporal shift. In that case, we have something called as dynamic time warping, which gives you how similar or dissimilar are two time series of mine. Let's move to our first clustering algorithm, which is k-means clustering. So we want to group our data into some number of clusters. In k-means clustering, we have to define the number of clusters k in which we want to group our data beforehand. This is also a drawback of this method. And we assign each and every data point to a particular cluster based on the distance of its to its centroids. So in k-means clustering, we will be having k centroids, and each and every data point would be assigned to cluster A if it is closest to centroid CA. Now, how do we find those optimal centroids to which that particular cluster data point should be assigned to? The algorithm would be discussed when we discuss k-means in detail. So the basic things are that our distance metric, which we use, is Euclidean distance over here, and the number of clusters are known beforehand. So because we are using Euclidean distance, which has a tendency to form blobs, spherical blobs, k-means clustering performs best when we have spherical blob kind of structure in our data. So the algorithm of k-means, by which we will be finding what is the optimal centroid which can make our cluster assignment optimal. We will be choosing the variable k, which is the number of clusters we want to group our data into. We will be randomly taking k, k centroids in our data points, and then we'll be iterating step by step to get better centroids. First, if you look at the objective function of k-means, this is the objective we want to minimize. That the data point is part of a particular cluster I, it should have the minimum distance from that particular cluster centroid. And the objective function is the sum of square distances of the data points in a particular cluster to its centroid, and would be taking a summation across all the clusters. So basically, we want to have clusters which are very compact, that the data points are very close to those clusters. This is what the objective in k-means clustering is. This might not be the best objective for clustering, but k-means clustering's algorithm optimizes for this objective. How to find the optimal centroids for this objective remains a question which would be answered in the algorithm. We choose k random centroids, then we assign each and every data point to a particular cluster based on to which centroid it is closer. Suppose in this example, to whichever centroid the data points are, it is assigned to that data point, assigned to that cluster, the centroid. After that, we take the average, the mean of all those data points assigned to that centroid to get our next new centroid. And this iteration goes on and on until we converge to our clusters. Just see the sample iterations we have. We are placing some random centroids. Then we assign. This is the assignment of data points based on whom they are closer to. Then the next iteration of centroids are the mean of the data points in those particular clusters. And in next step, we find that if we take the mean, if we take the new cluster assignment and we take the mean again, the centroids almost get converged. This is just an example of how you implement it in Python using sklearn library, and you can just three to four lines of code can implement it. We would be discussing implementation of k-means in a hands-on demo we would be doing later. Before moving to how good this clustering is, I just want to show how the k-means iteration algorithm works. Suppose these are the data points we have. Let's take in two dimension so that we have a visual example to understand what is k-means doing when it tries to find the best clusters. Let k is equal to 3, we initialize the k we want. Let's have a Starting point of centroids has mu1, mu2, and mu3, which is visible. If we move to next step, these are the new centroids assigned based on the mean value of all those cluster points. Now these new centroids got assigned. In the next step, we would be assigning each and every point to the closest centroid and again taking the average of the new assigned points. If we assign those points to the closest centroids and took the average, then this comes as the cluster assignment we know. To the next step, let's wait when does it converge. Move to the next step. Again, the clusters to which some points got assigned changed. In this one, 2 points changed their cluster. Again, the points moved. Each centroid was shifted to the mean of the newly assigned uh, cluster data points. Again, 2 points changed their cluster. Let's wait when does it converge. 1 point changed cluster this time. Now no points are changing cluster. If we keep doing new next step, no new centroid or cluster assignment will happen because the k-means algorithm got converged. This was about k-means algorithm. How does it iterate over the steps to get into the converged centroids? So we walked through the k-means algorithm, which was doing iterations to get to the best centroids we have so that we converge in our clustering. After we have done our clustering, how do we evaluate our clustering? These evaluation metrics are the metrics we can evaluate when we have the constraint that we don't have labels. Suppose we have labels in our test data set, then we might also want to evaluate through whether the clusters my clustering algorithm has grouped my data into is aligning with the true labels I have or not. But suppose we don't have the true labels, what we can question the cluster is whether those clusters have some good geometries or not. First one is distortion, which is basically the distance of each points to its centroid, which k-means algorithm itself optimizes for. What it tries to say is whether my clusters are very compact. The data points which are in a particular cluster are around that centroid's neighborhood or not. Another one is Silhouette score, which tells me both of the things, whether the data points in the clusters are compact and close in its neighborhood or not, and also what's its mean distance to the another cluster, so that clusters are well separated or not. One point is clusters are compact or not, and clusters are well separated or not. Silhouette score can be found for each and every data point in the clusters I have formed, and can also be used to investigate which all data points are causing my clustering algorithm to not form good clusters, or which of those points are outliers maybe. That can also be investigated because Silhouette score is being found for each and every point. How much distance does that point have with its own centroid and with the other cluster centroid? Another metric is Kalinski-Harabes score, which is at a cluster level and hence can be found out in lesser amount of time compared to Silhouette score, which is aggregation of many point level metrics. Over here, we find something similar to Silhouette score, but we are not normalizing by the maximum of the within cluster distance and between two cluster distances, but we just take a ratio between how much of scatter is between two clusters and how much is within that clusters to get my score. So these metrics tell me about the geometry of the clustering that has been done by my algorithm. As my k is a hyperparameter, I would want to choose a good k. How to choose a good k? Again, we don't have a particular deterministic method, but a method which is used practically is called elbow method, where you want to find k. As we increase the number of groups to which I want to cluster my dataset, my distortion would be decreasing. The distance of all the data points in a particular clusters to its centroid, the sum of those distances would always be decreasing with amount of k. But I cannot go on increasing my k. So we observe the point where increasing k starts giving diminishing returns because we have already reached very good compact clusters at that point of time. And that is how practically k is decided. This might not work always, but this is one of the methods to decide k. And instead of distortion, we can have look at any other metric like Silhouette score. There are cases when k means fails. Obviously, as we talked in introduction of k means itself, that we have to initialize k beforehand, and Euclidean distance will work best when we have spherical blobs. And you can see the examples where k means clustering is failing when you don't have spherical blobs, the density is very different, or you have outliers. We can have a smarter initialization of our first centroids, because if our initial centroids are placed at some weird positions, then the number of steps k-means would take to converge would be higher. So one intuitive thing we can do is, if we pick first random centroid, we would not want to pick other centroids close to the first centroid we picked, so that we have diverse centroids and we can cover more space, and we can cover assignment of different data points. Suppose in this case, if we have three initial centroids, if we have three initial centroids over here, then the assignment which will happen, many data points can be assigned to this centroids cluster, many data points can be assigned to this centroids cluster, and those assignments will be very far away from the true clusters. Compared to the case if we assign our centroids as they're assigned through these crosses in the figure, these initial assignment can be much more helpful, because we added a bias while deciding our centroids. After putting our first centroid, we decided to have next centroid farther away from it. So we sample our centroids with a probability proportional to d square, where d is the distance to the nearest chosen centroid which we have already initialized. Basically, we want to sample centroids as far as possible to get better convergence. This is k means plus plus. Key takeaways we have from k means are that the convergence can be a problem if our initialization of centroids is not good. We have to have k initialized, and for a lot of cases, k means might not be the best method to use. So after K means, what next topics are there are hierarchical clustering and DB scan. After DB scan, we would be discussing about Gaussian mixture models, which does not provide us with only hard boundaries of clusters, but about how much a data point can belong to one cluster and how much it can belong to some other cluster. Basically, we assume the probability distribution. Now, the two disadvantages of k-means were we have to select k upfront beforehand, and another was it only works best in certain kind of data structures, and it might not work well when we have rings or some chains in our data sets. Now, if we want to solve for the first thing of k required beforehand, we would want to let our data decide it. Let's discuss one kind of hierarchical clustering, which is agglomerative clustering. In agglomerative clustering, what we do, we think each and every data point in our data set is a cluster. After that, we would be starting to merge each and every data point to form one cluster. Suppose we first merge two data points to form one cluster. Similarly, other data points form some clusters. Now, we will also be merging any two clusters. Similarly, as we merged any 2 points which we believe to be a cluster of its own. How do we merge? We merge based on some distance. Whether these two should be merged or not depends upon what is the distance between those two clusters. In our first stage, we have capital N number of data points, we have capital N number of clusters. As we go on merging, we can keep a threshold of how much close two clusters should be to merge them, and this can help us decide our k, the number of clusters we want, by using this threshold. Especially hierarchical clustering can be applied in cases where we have some kind of hierarchy in the clusters we want, that these are the groups, then we have these subgroups, then we have these subgroups. Because of the nature of hierarchical clustering algorithm, we can get hierarchies or groups and subgroups naturally because of the intermediate steps of the algorithm, as we will see. These are some of the applications at Amazon of hierarchical clustering. As you can see, it is used in grouping search queries and product categories and subgroups. If you look at this picture, this is a dendrogram, and what it means is, suppose we have all these points 0, 4, 1, 7, 6, 8, 5, 2, 3. We are merging 2 points based on the distance threshold. On this distance threshold, which point should be merged? Point 0 and 1 had a distance which is lesser than this number, so they were merged. 6 and 8 had distance which was lesser than this number on y-axis, the distance axis, hence they were merged at this distance. In this way, after we have been merging different clusters because their distance is above a certain threshold, we can select k by cutting this dendrogram at any point. Suppose we cut this dendrogram at this distance, we select this distance to be the threshold. Our k would be 3 because we have these 3 clusters. Suppose we want to decrease our k, then I will be moving upwards so that merging of these two clusters also happen. In agglomerative clustering, we select a height, we cut at that height, and that height gives us the number of clusters k we want to have. After seeing this structure, we can see that how much change of distance threshold happens for merging a particular cluster. If we want to merge these two clusters, then we have to go through this large gap. If we want to merge these two clusters, then we have to go through this small gap. So there was a lot involved in merging these two clusters. Hence, we can say when we had k equal to 3, and if you want to go to from k equal to 3 to k equal to 2, then the clustering might lose more compared to when we want to go from k equal to 2 to k equal to 1. And we can intuitively see that the larger the gap is between the two merges, we would say that the clustering in between these two boundaries was the best clustering almost. Almost similar to how we were using a elbow method to find k, but unlike k-means, this is the part of our algorithm only that we build the dendrogram by merging points and then clusters till the end that we get capital N clusters to a single one cluster, and we can cut at any threshold we want to select, uh, and then we get k number of clusters. And also, k-means was using Euclidean distance as a distance, and hence it was doing good on spherical clusters. But over here, we have the freedom of choosing any other distance we want to decide which two points, which two clusters to merge. As you can see, there are different distances. Suppose we say single min distance. This is the minimum distance between any 2 points of these two different clusters. Maximum distance is the maximum distance between any 2 points of this cluster. Average distance is the pairwise distances of all the points in these two clusters, and we take an average of all of that. Ward is a distance which measures if we have these two clusters. This cluster has some variance, the intercluster variance. This cluster has some variance, the intercluster variance. If we take both clusters together, if we merge these two clusters to make one cluster, what would be the new variance? Is the sum of variance and the new variance of a complete cluster getting increment? If the cluster variance is decreasing, if the cluster variance is increasing too much, then we say that we would not want to merge these two clusters. It is very similar to what k-means algorithm was optimizing for, but there we have an iterative algorithm. Here we greedily go and find should we merge these two clusters, what would be the variance after we merge these two clusters. So the ward distance is for that. We would see these kind of distances can help in which cases. And again, just like k-means, hierarchical clustering can also be implemented in Python with just few lines of code. Let's see why example, if we want to use some distance, how is it helping us? As you can see, we should have these two clusters, and this is kind of a different cluster outlier. Let's select our linkage distance to be what distance and get our dendrogram. Okay, we've got our final dendrogram, and you can see the largest gap appears to be between these two merges. What it is telling me is that getting these three bridge points into the second rightmost blob is not costing it much variance, because this is where the merging of those three midpoints is happening with this bigger blob. If you see, this merge is not taking much of a gap. Let's try out min distance, but before that we should observe that merging of these 3 points is not of a, is a small gap. Merging of this whole blob with another blob is a very large gap, as you can see. Let's change it to single, which measures the minimum distance between any of those 2 points. And you can see that if it measures minimum distance, then the minimum distance between this point or this point, minimum distance between this point and this point. Let's see what is the cost we would incur in merging whole of these blobs into a single blob. Because as you can see, if we want to use min and our data points are in shape of chains, then merging those chains through these bridge points would become very easy, because it looks at the minimum distance. But if we were looking at average centroid distance, then average centroid distance between these two things are large. Let's try using min with the previous case we had and check what happens. If we use WOD, again, this is a small gap, but merging the whole thing into one blob is a very large gap. Let's see in case of min. So merging these three bridge points into this blob is a larger gap, but merging this whole thing into one blob is a smaller gap. So this distance things merging the whole blob into the all the data points into a single blob is much less of a penalty, but it is not actually. And WOD is a better choice over here, because we don't want to connect these two clusters with these bridge points. Let's take another example. Let's run it with WOD. You can see merging all these clusters into one is having such a large gap. And all these points belong to only one cluster, which is the shape of S. So this should not have been such a large gap to merge all of these data points into one cluster, but it does in case of WOD, which is kind of k-means algorithm, which is not good for these kind of non-spherical blobs. Let's try out single min. Over here you can see merging the whole set into a single blob is not much of a gap. It's a very small gap. So min has been proved better in detecting the whole data point set to be one cluster. But in these kind of cases, DB scan also performs well, which is based on density estimation. We will move to DB scan next. So DB scan is based on density estimation, and especially it can help us in cases where the data structure are not too much structured or kind of in spherical blobs where k-means actually performs well. Hierarchical clustering helped us solve the problem that k need not be initialized, but also based on different distances, it is not able to perform good on these kind of density based clusters. So if we want to cluster these density based clusters, we would want to quantify some entities which are themselves small densities or small blobs, and we are extending those blobs. We will see how DB scan does this. So what DB scan does is it selects some core points. Core points are defined as points which have some minimum number of points in its epsilon neighborhood. Again, those minimum number of points and epsilon are hyperparameters. About what we call as good density depends upon my minimum number of points and epsilon radius. And then I go on extending that density of mine to get the clusters. Okay, core point and border point are points which are within epsilon radius of a core point, but they themselves have less than minimum points neighbor in their own neighborhood. And then we have noise points which are not near any core point and also have less than minimum number of points in their neighbor, which are mostly outliers in most of the cases. If you see DB scan algorithm, it goes on to estimate the density of data points starting from some small blobs, and then it gets to finer final clusters. And again, DB scan is implemented in Python through very few lines of code. Let's see how DB scan algorithm performs with different epsilons. Okay. In this data set, if I run DB scan and k-means, let's see what happens. So DB scan was able to detect the correct clusters. If you go through how DB scan works, it is getting some core points. Everything green over here would be core points, and the border point would be denoted by oranges, as you can see in this legend. You can go through each and every step of, and it is able to detect the core points which form the part of the density of my data. Then it goes to different core points. And let's see how this is sensitive to my epsilon, because my epsilon defines how much close they have to be to form an entity of the density I want to estimate. You can see the effect of epsilon. If I keep epsilon to be 20, then I'm not getting good clusters. There are points which are becoming outliers just because they are not so close to core points, which should not be the case. Finding the optimal epsilon again becomes a question over here, like it was k in k-means. We use elbow method again, like if you see this plot of k with different epsilon is on y-axis, you can see the elbow coming over here, and let's see where the elbow is. It comes at a point where we get good clusters. So again, elbow method helps us to find that optimal point where we get an epsilon, which helps us to get those points in the neighborhood of core points, which helps it make those blobs, extend those blobs to estimate this density. So DB-scan algorithms helps in density estimation, and it is performed by these two parameters of epsilon radius and minimum number of points to be in their neighborhood. This was an example to show you how epsilon is important for us. and dbscan can be easily implemented in Python. And this shows how we use the elbow method again, the distance plot again to find epsilon as we were using it for finding k. And k means dbscan has a lot of strengths. We don't require the k, it can find arbitrary shaped clusters, and also it can also help us find outliers which are inherently part of the algorithm, those noise points. And it has some limitations as well, that again it has hard boundaries as any other clustering algorithm we discussed. And border points are kind of probabilistic. How we go on with the algorithm would change those border points. These are two main uh, disadvantages of KME DB scan. And on evaluating clusters, we already discussed these metrics where we don't have labels. Let's discuss some metrics when we have labels. When we have labels for my evaluation set, I would want my clusters to align with the labels I have. So I can just find the alignment between both of them, which is found using adjusted rand index. We're short of time, so if you are curious about it, you can refer some blogs to read more about it. Normalized mutual information basically tells how much information do I get about the true labels from the clusters I have, as you compare two probability distributions using some metrics like KL divergence or cross entropy. Over here, it's kind of a proxy for that. This is about what metric you can use in which algorithm. But let's talk about what's still missing. What's still missing is we don't have an assumption of what distribution my data can take. And some points can belong to a particular cluster with some probability and some other cluster with a different probability. Let's say a document can span multiple topics. We want to know how much of it spans different topics. In that case, we cannot have these hard boundaries as the clustering algorithms we discussed. So next we would be discussing Gaussian mixture models, which my colleague Dhruv would be teaching. Thank you. Hi everyone. Let's go through a small demo in Python notebook to visualize how normal k-means clustering is clustering our dataset, and just see how we are going to evaluate the clustering it produces. I'm just installing few libraries which is going to help me do the k-means clustering. Over here in this cell, I would be loading some distinct digit images. We're taking these simple images so that k-means cluster are interpretable, and we get an intuition of what the centroids even mean in case of images, and is it able to cluster properly, because we have an advantage that we know what label does each image correspond to, which means we know the number which is being represented by that image. Let's load it. So we have some images. Images are of digit 0, 1, 4, 6, and 7. Now, these are 8 cross 8 images, and images are being represented using pixels. If we flatten 8 cross 8 image into a vector of 64 dimensions, we can think of it as a feature vector, and we would want to cluster all these feature vectors by k-means to see what happens. Is it able to cluster all the 8s together, all the zeros together, all the 4s together? Let's see. I use k equals to 5 because I already know that There are five labels, and let's use k equals to 5 and see what kind of clusters it produces. And before clustering, I applied a normalization on the feature vectors. Then we use a skill and libraries. K means clustering with n clusters equals to 5, and we fit on this data to get the clusters. And what I am measuring over here is cluster purity, which means in each and every cluster, if majority of the data point belongs to a particular number, a particular digit, then what percent of that cluster belongs to that particular digit? So cluster 0 is 86%, 6, cluster 1 is 96%, 7, cluster 2 is 99%, 0, cluster 3 is 91% pure. Just see, the digit 0 is very easy for our algorithm to cluster because digit 0 would not have much variance if we represent it through images. But 6 can be written like this, 6 can be diagonal, or any other number if you take, for example 1. Different images of the number 1 can have very little variance of variation, unlike the number 6. It's harder to capture for the algorithm. As a human also, you might get an intuition why is it harder to capture for the algorithm. Let's visualize what my embeddings, my 64 dimensional vectors are being grouped to. So what I'm doing over here is TSNE visualization. TSNE is a method which you might have been taught in dimensionality reduction module on projecting those feature vectors to two dimensions. This is when I will color those feature vector embeddings by their true labels. This is what I get. And if I don't know the labels, I cluster using k-means. These are the clusters that I get. You can see it is able to almost capture which data point are going to belong to which clusters. Some exceptions are there, like this has been marked green, this has been marked orange. Okay, let's have a interesting observation. If it says the k-means algorithm says that these all data points belong to a single cluster. Let's see what does its centroid look like. Because we have images with us, we can visualize things. If you see the centroids are looking very close to what that number would look like. For one, it has kind of merged or averaged out how different one images would look like. For 4 also you can see it has averaged out, but 6 and 7 is and 0 is also very clearly visible. And let's say if we used elbow method to get our k, would we have been successful in this kind of data or 64 dimensional data? It will plot the different distortion values and silhouette score values for different k values. You can see that we don't get a sharp kink or sharp elbow in our plot. Similarly, the silhouette score plot is also up and down without any proper conclusions. Why does it happen? It happens in one line because of curse of dimensionality. We have gone in higher dimensions. What we were calling Euclidean distance in lower dimension, the same notion might not remain in higher dimension. And why Silhouette score is coming so low despite having 94% accuracy? By accuracy, we mean we knew the labels and we saw the purity of our clusters. It's mainly because of the inter-cluster variance being very high. The images belonging to the same digit have a very high variation, and also they are in a very high dimension. In 64 dimension, the distance blows up. Also for it relatively blows up, and despite having good clusters, we will be getting still hot score to be very low. You can see over here the intra-cluster distance is 8.06, the nearest cluster distance is 9.87. So even one cluster's intercluster distance is very similar to its distance with another cluster. That's just because of we operating in a very high dimension. In very high dimension, it's very difficult to relatively compare between two distances or two Euclidean distances. If we think of applying a dimensionality reduction algorithm called PCA to reduce our feature dimension and then again calculate Silhouette score by using k-means, let's see what happens. You can see on different dimensions, we can see as dimensions are increasing, the score is becoming less, despite the clustering accuracy being around the same number. And you can see what Silhouette score looks like at different dimensions. As we increase the dimensions, Silhouette score is decreasing, not because of our clustering being bad, but because of our dimensions being very high. So we got a few takeaways from this. How is k-means performing good in these kind of intuitive images, and also how cursive dimensionality can lower the Silhouette score despite the clustering being very good. So if we have labeled data, we should always prefer labeled data to do evaluation of our clusters. Thank you. I hope the demo was helpful.